Okay, so we did the one-dimensional case, and we saw some of the basic ideas: bound charge, internal fields, external fields, polarization. Now let's let things get more complicated. So if you do other geometries, those can lead to non-uniform P, which can lead to great excitement. So we're going to see new things when we let our polarization become non-uniform. All right, so let's just pick another geometry. Let's put a point charge, and I'm going to call it Q free, right? Because this is the charge that creates the effect, QF, Q free, inside a dielectric sphere. Now let's just see what happens. Okay, so dielectric sphere, and there's the point charge. I won't label it because I got to draw a lot of field vectors. Okay, so you know what a point charge does. It makes a field sticking out. And now it's not really that it's making a field and we're putting a dielectric in the field. The dielectric is automatically all over the field. It's everywhere. So if we think about it, we know this is going to make an electric field pointing away because it's positive. So that's going to attract the negative charge, and it's going to push away the positive charge. It's going to create little dipole moments that are going to point out. And then the volume of the dipole moments and the size of the dipole moments will be bigger when you're close to the charge, and it'll be smaller when you're far away from the charge, because the electric field the charge creates is bigger and smaller. So the P, the polarization you would end up with, the dipoles per unit volume, would be big when you're close and get smaller when you go far away. Big when you're close, big when you're close, big when you're close. I could do them with field lines, it would be better, but I've already started drawing vectors, okay? And it gets smaller when you get farther away. And it gets really small when you get really far away. Okay, so that's the P, that's the polarization field inside the material, okay? And it's not quite making it to zero, it still exists a little bit at the surface. So what's that going to do? First, it's going to create sigma B, right? If this thing is pulling negative charge, sucking it towards the positive, if the positive charge of Q free is sucking a lot of the electron clouds in, it's going to leave the outer part positive. It's going to leave a charge density on the surface. And we know the formula for that is P dot n hat. So as long as there's some positive, or as long as there's some P vector that remains on the surface, I drew it decaying too rapidly. Okay, we can draw it like that. There you go. So there's some P field remains on the surface. You dot it with the normal direction, which of course is the same direction, and you get that the charge density on the surface is just the value, the magnitude of the polarization of the surface, okay? But something else happens, and something else happens inside the material. So now let's imagine grabbing a little piece of it that looks something like this, just a little radial sort of a slice, right? So it kind of looks like that. Oh, whoops. I'll blow it up a little bit, kind of like that. Some three-dimensional piece coming out of here. If we looked at it, we'd say, actually, here the P, the polarization field, is kind of bigger on one side than it is on the other side. Right? So if the polarization field is bigger on one side than the other side, what's that going to do? Well, when it's big, it pushes a lot of charge. So if we were to imagine, let's see, is there going to be negative charge on this surface? Right? Polarization's that way. It means negative charge gets pulled this way. So you'll get a bunch of negatives. I'll say 3, 4, 5, 6. I'll draw 6 negatives on that surface because they're being attracted to the positive. But out here, where it's weaker, maybe there's only 3 positives, right? Because the polarization is smaller and it's the same surface area if I drew it right. So this volume, so the volume has a net charge. Okay? It's a neutral material, it's just a neutral dielectric, but net charge is being created within the volume. So it also creates what we call rho B. So volume charge density that's equal to minus the gradient, or minus the divergence of the P field. Okay? So these are general results that you can calculate with a lot of vector calculus and field theory. I'm just kind of giving them to you, but they kind of make sense. You can see how, well, we talked about this one. Let's think about this one for a second. If you're really into field theory and you understood Unit 1, you can kind of see how the divergence of the P field has to do with creating the P field, right? So it is bound charge that creates the polarization field. Or if you just want to think of it as a derivative, right? If you're not as quite into the vector calculus, but you understand this gradient or this divergence is a derivative, you can kind of see the amount of bound charge you get in this little element. If you shrink it down, it's the difference between how much is on this side and that side. It's the difference in P. It's delta P, delta X. So it's a derivative. And this is just a derivative. So whatever level of vector calc you're into, hopefully you can see that that's what goes on. And you might say, how can it create charge if the thing is neutral? And in this case, the answer is they cancel, right? So the amount of surface charge you get, the total amount of surface charge, in this case, would be positive. You're going to leave positive charge out there, and everywhere you go on the inside, this is going to come out negative. So if you were to add all up the bound charge, it would all add to 0, because the thing actually does have to be neutral in sum.